The James Webb Space Telescope is causing quite a stir. It's making us rethink everything we thought we knew about the universe's beginnings. Physicist Michio Kaku summed it up perfectly last year. Everything's shaken up because of the James Webb Space Telescope. We might have to update every single textbook on how the universe was formed. So, get ready. Our understanding of the cosmos might be about to change. Creating a galaxy like our Milky Way is an incredibly slow process. It takes billions of years for a galaxy to form and grow to the size of the Milky Way, which has around 100 billion stars. But here's the surprising part. The James Webb Telescope has found 6 galaxies, just as big as the Milky Way, that existed only 500 million years after the Big Bang. That's just a tiny fraction of the universe's age. This discovery is a big mystery. According to our current understanding, galaxies that big shouldn't exist so soon after the Big Bang. So, we might need to rethink our entire theory about how the universe formed. There's definitely something here that doesn't add up, and it could mean we need to update our ideas about the cosmos. Astronomers are having a great time discovering new things thanks to the James Webb Space Telescope, which has been up and running for almost 2 years now. This powerful tool is pushing the limits of what we can see in space. Recently, it's found some surprising things about the early universe. For instance, it spotted galaxies that are way more developed and massive than scientists previously thought possible for that early time, just 500 million years after the Big Bang. One galaxy in particular might be one of the oldest ever seen, and it already has billions of stars. The Hubble Space Telescope discovered this colossal celestial body as a peculiar point of light in its range of view just 2 years ago. Prior to directing Webb towards it, scientists were unable to fathom that this peculiar point of light was actually a gigantic galaxy teetering on the brink of time. The point of light turned out to be a primeval galaxy far larger and older than expected. According to Webb studies, at a redshift of Z equals 9.3, or just 510 million years after the Big Bang, we can view this galaxy, which is known as GZ9 P3. Although we have detected several galaxies in the 350 to 500 million years after the Big Bang era, none of them have been seen with the same magnitude as this one. These results suggest that the galaxy's stars were generated at a faster and more efficient rate than previously thought in order for it to reach its present size. Not only that, but GZ9 P3 has an unusual shape that may be disclosing primordial cosmic mysteries. 2 bright spots inside the galaxy, which the discovery team interprets as signs of 2 dense nuclei, indicate a galactic merger. That 2 early galaxies may have collided in the early cosmos is a very real possibility. Not only did the researchers determine the shape, age, and mass of this old galaxy, but they also focused on its stellar population, discovering that the picture is dominated by young, brilliant stars and the older stars of GZ9 P3. The JWST allowed the research team to identify elements like silicon, carbon, and iron. Star explosions release the heaviest element a star can make, iron, into space, filling the early cosmos with metals that will later form stars. It was also discovered that GZ9 P3 included a higher number of old stars than anticipated, which could indicate that galaxies reach chemical maturity at a quicker rate than previously believed. Stars likely formed considerably earlier than previously thought and had aged sufficiently by this cosmic period, casting doubt on our present knowledge of galaxy formation. In light of these results, a new model might be needed to account for the enormous size and chemical maturity of galaxies, as well as their quick expansion into these states. Additionally, they imply that right after the Big Bang, galaxy mergers might have been the most common cosmic event. These galaxies are more massive than was previously believed possible. Thus, although our present cosmological framework might not be wrong, our knowledge of the rate of galaxy creation probably requires updating. Our cosmological model is based on mathematically supported ideas and data, but there are still hints that something isn't quite right. The crisis in cosmology is a term you might be familiar with. Basically, this problem arose when various ways of calculating the expansion of the cosmos began to produce conflicting findings, and they still do. Because cosmologists don't know, Recent findings from the James Webb Space Telescope have exacerbated this situation. As a result of cosmic expansion, faraway galaxies are getting ever farther from us. What we obtain when we use the cosmic microwave background, CMB, the light left over from when the universe was just 380,000 years old, to compute the rate of the universe's expansion is this. Then there's the other approach that compares the apparent brightness of faraway supernovae to the expected brightness. We also get the rate of cosmic expansion from this, which is known as the conventional candle technique. The Hubble constant is the name given to the rate of expansion. On the other hand, the cosmological crisis is the Hubble tension, which is the difference in findings between the two approaches. However, it is no longer the exclusive crisis. Our theories are being tested to their limits by a brand new cosmic conundrum. My entire life has been devoted to refining a single hypothesis of the cosmos, and now even that notion is under scrutiny. This is exactly how science advances. Therefore, I'm all for it, Kaku remarked. Countless stars can be seen when one looks up at the sky, provided that they are not in a metropolis where light pollution is a problem. The Andromeda Galaxy, which appears as a faint dot among the stars, may possibly be visible to you. Planets, galaxies, and stars abound throughout the cosmos, which is why their size in relation to the cosmos is an open subject. Just how much stuff is there? Current cosmological observations disagree on the distribution of matter in the present-day cosmos, which largely causes this conundrum. The new cosmological anguish, or the enigmatic S8 tension, has emerged as a result of this. The clustering or lumpiness of matter in the universe is measured by the S8 tension. To simplify, think of space as a gigantic jigsaw puzzle with pieces of matter all over the place. The distribution and clumping mechanisms of this substance are of interest to scientists. Two metrics can be used to evaluate this. One approach is to make use of measurements made at low redshifts, such as those made possible by weak gravitational lensing, in which light from farther away is bent and distorted by the enormous gravitational pull of huge objects like galaxies and black holes. The second approach uses the CMB-based standard model of cosmology. The S8 value that comes out of these two approaches, meanwhile, isn't consistent. At its confusing core, the S8 tension is this disparity. Our next move, even with all the hypotheses, observations, and made-up things that back them up, shows that something is obviously off. A massive cosmic simulation ran by one of the world's most powerful supercomputers helped scientists fill in the gaps. Over 50 million hours of computer time, spread out across 30,000 processors, were needed for this Flamingo project. A somewhat confusing term, Flamingo stands for Full Hydrodynamics Large-Scale Structure Simulation with all-sky mapping for the interpretation of next-generation observations. Even though it accounts for only 20% of the universe's mass, conventional bionic matter is included in Flamingo. In contrast to previous simulations that solely considered dark matter, Flamingo follows the effects of both dark matter and the galactic winds caused by supernovae and supermassive black holes, which may slow the expansion of galaxies. Even while Flamingo accomplished a lot, such as correctly predicting how the Milky Way and Andromeda galaxies formed, it was unable to fix the S8 tension, which was its intended problem. In fact, the simulation runs counter to what Webb and other telescopes have found about the distribution of stuff in the cosmos. The present idea provides a lovely explanation for galaxy evolution, but it has a flaw. It suggests that the true density of galaxy clusters is 7% lower than what is actually observed. There is still a 5% excess clumping in the Flamingo simulations, no matter how detailed they are. The Hubble tension is real, according to recent observations from the Webb Space Telescope, which lend credence to the results obtained by the Hubble Space Telescope. The so-called Hubble tension is worsened because Hubble's estimates of the rate of expansion of the cosmos are correct. The Hubble constant tells us how fast the universe is expanding, but it doesn't match up with the data we have. We still don't know why this mismatch happens, but it might mean we need to rethink some of our scientific ideas. Some even suggest we could be wrong about dark matter. What do you think? Share your thoughts in the comments, and don't forget to subscribe for more updates.